the record for your end. And
Yeah, sure.
yeah, I think okay. Yeah. Okay. So let's get started. So today is a great honor, pleasure to have Anant speaking for us. So Anant got his master's degree at IIT Kharagpur and then moved to University of Minnesota, where I met Anant before. And so not only Anant got a degree in geophysics, but also get a interning experiences in San Francisco. And then he moved back to India and now working at Nissan uh, in the southern part of India. And we're the digital center that deals all types of the data from Nissan company. So today, Anand is going to share with us some of the work that he's working on, as well as the uh, the institute, I would say, the team that uh, uh, the business that they are running on. So with that, I will give it the rest time for Anand. And yeah, you could control time by yourself. We are quite flexible. And at the end of it, I think some of the audience are going to ask to interact with you to for the topic that we are interested in. So Anand.
Sure, Johnny. Thank you for the introduction. So let me start. A quick bit about me. So I completed my education at the Doon School, Dehradun, where I was in a boarding school for about 4 years. I learned a lot there, and I played squash for my state. I picked up guitar. So a lot of hobbies, a lot of development. And then I went on to study in IIT Kharagpur in geology because I was always interested in science. So geology is the major that I picked. And due to my mathematical bent of mine, which is like less mathematical in nature to geophysics. Currently, I am working as a lead data scientist at Nissan's Global Digital Hub in India. We work with the Japan global headquarters and also different regions such as Europe and North America. So it's pretty much a global hub, and we are working for the internal business of Nissan. Previously, I've been associated with a lot of organizations. So with Kane, National University of Singapore, University of New South Wales, NMDC, which is a Government of India initiative and an organization, and Lofty, which is an advertising technology company. So today I will be talking mostly about time series forecasting. So time series forecasting is very important in machine learning in general because of the value that it creates in the business. So demand forecasting and sales forecasting are some of the initiatives that are, I think, critical in almost all different businesses, because the final outcome is you need to be able to make profit, and for that you need to have good sales, right? So being able to forecast sales effectively helps in planning better, reducing the inventory costs, and so on. So this talk is not going to be very academic. I will go over some of the industrial things that we see and that I've experienced during my last 2 years as a data scientist. So let me start with a quick poll. In this picture that you see, what would be a good caption to describe it? So you can maybe write your answers on the chat.
So could you raise your question again?
So the question is, what is a good caption for this image? might have already heard the caption, but looking at this image, can you recall what this is saying? Yes, that's perfect. By Sani. Data is the new oil, right? And this is by an article that was published in The Economist. We can see different corporations, and now, like oil was in the 19th and the 20th century, now data is the new oil. So what is it exactly that makes data so precious, and how do we use data for insights? So Peter Norvig had said that we don't have better algorithms, we just have more data, right? But in addition to data, you also need the data to have a good quality. So this series of chats depicts that, even having data at the end, it's just a giant house of cards. Because if the data input is not consistent, and the data input is varying in nature, the data pipeline and the machine learning pipelines all might fail, right? So the best practices are to have structured data systems instead of manual preparation and maintenance of data files. So a lot of businesses, I think in today's date, they work on Excel sheets, storing the data manually. So that's the first thing, to have good structured data systems and have a good data engineering team. The second best practice is have a good data governance model. That is the who, what, how, when, where, and why of data. So governance will effectively help different parts of the business. So the sales team, the finance team, the marketing team, all have their own data that they store, but visibility of this data into a common platform so that the data science team can use it. I think that is one of the primary ways to accelerate the data science process. There was a report by BCG which claimed that only 10% of the companies today are able to actually have any sort of financial success from AI. And there were several reasons behind it. I mean, data is one of the key things there. The third one is, again, more interconnected data teams so that there is more collaboration and the data sources are richer. So coming from data to data science. Now, what is data science? Some Twitter definitions as of 2014. A data scientist is a statistician who lives in San Francisco. Data science is statistics on a Mac. I'm using a Mac now, so it's probably, yeah, that makes me a data scientist. And I also lived in San Francisco for about three to 4 months. So yeah. And the third one is slightly better in terms of its definition. So someone who is better at statistics than any software engineer and better at software engineering than any statistician. But in reality, data science is a combination of computer science, maths and statistics, and business and domain expertise. So this is a very good Venn diagram. And also in terms of how data science can be used is there is descriptive analytics. That is just to look back at the data and then say, what was the sales that I had? Then there is diagnostic. That is, how do different variables actually affect my target? So if my target is sales, how does, say, government policies affect sales? How does the GDP affect sales? So that's kind of a diagnostic analytics. Then there is predictive analytics, which is the most popular, encompassing machine learning, statistics, and so on, and prescriptive as well. So predictive and prescriptive go hand in hand. And the last choose your own data science adventure. This is by Cassie Kozyrov, who is the chief decision scientist at Google. So the first question that she's asking here is, you want machine learning? If the answer is yes, that means using data. The next question is using data. If there is a lot of data, then only we can proceed further. If we don't want to use data and you want machine learning, then there is no way to proceed, right? So only using lots and lots of data, we can do machine learning. So that's the first input from here. After that, the second question is how much data, right? If there is only a few data and there is uncertainty, right? It goes on to say that you want statistics. Otherwise, you want data analytics. So just to simplify this, data analytics is about understanding the data, that is descriptive and diagnostic data science. But machine learning is more about predictive and prescriptive. So what is machine learning? Machine learning is an approach to automating repeated decisions, right? So here we are automating certain decisions that involves making algorithms that find patterns in the data, and then they should be able to generalize well. So they should be able to deal with brand new data. So the first thing is finding patterns, and the second thing is the ability to generalize. So here, let me take an example. Suppose we have a treatment schedule of patients, right? The first day, there should be 28 mg, which should be administered to a patient. The second day, there should be 17 mg, and so on. So what should be the dosage for day 2? Can you write the answer in the chat? So let me repeat the question. If we have a treatment schedule, which looks like this, what is the dosage for day 2? Okay. So the dosage for day 2 is simply 17 mg, right? So if there is a question about um, historical data, then we can directly say that the dosage will remain the same. Just look up the table. But machine learning comes in where you're dealing with new situations. So if the question here is up to 60 days, this was the particular dosage, but what should be the dosage on day 61? So there machine learning can help. But even then, it's a can help. It's not a will help. So we don't know for sure whether machine learning will be able to predict it. And why is that? That is because here we are assuming there is a inherent pattern in the data that machine learning should be able to uncover. But if there is no pattern, then the problem is defunct. It's not solvable. If there is a pattern, then machine learning can help us, but only if the conditions post day 61 remain the same. They can slightly change, but in the event that the complete scenario changes, so for example, the patient undergoes a new disease, and that disease conflicts with the current medicines that he's taking. So day 61 will completely change, right, in the terms of dosage. So the conditions should only slightly change or they should continue. Then machine learning would help. So why should we look at forecasting? So that's the main topic of today. Forecasting is everywhere. As I talked about sales and demand forecasting, the annual potential value is up to $18.5 billion. So this is as per a report of McKinsey that was published last year. The second most popular use case, which all of us know about, is weather forecasting. Marketplace forecasting is another use case by Uber, where they try to match the demand and supply of cars in different places. So this is a representation of the San Francisco Bay Area. Then we have COVID-19 forecasting. Forecasting the race for the Senate. This is an interesting use case, right? And we have tourism forecasting. So this particular chart and the bottom right it's showing due to COVID, when would the tourism actually recover? So there are three scenarios in July, in September, and in December. So this is as of 2020. Right? So forecasting is everywhere, and it is a very good use case. Uh, but why machine learning for forecasting? Why should we use machine learning? I mean, just looking at the trends and seasonality, we should be able to forecast, right? Machine learning comes in because now we can take in additional data. We can take in a lot of data and be able to forecast even better. So it's like a competitive edge that comes in through machine learning. The next question generally, like naturally, is what can be forecasted, right? So the below factors determine it. The first factor is we should understand the factors that affect the target variable. We should have data. And the third one is if we forecast something, will that in turn affect the thing that we are trying to forecast, right? So the first one is factors, the second one is data, and the third one is whether what we are trying to forecast is directly affecting in turn itself, right? So let me go through two examples. The first one, we are looking at electricity demand forecast, and the second one, we are looking at foreign exchange rate forecast. So in terms of electricity forecast, what all conditions would be satisfied? Do we understand the factors that affect the target variable? Yes. I mean, if we know that electricity demand is directly tied in to the weather, right? If it's a hot weather, we generally use more air conditioners. Refrigerators are more in use, and so on. So there is a direct correlation, and the factors that affect it are well known. We have a lot of data available as well, and the electricity demand, the values of the forecast will be independent of the forecast. So if I say that tomorrow's forecast of electricity would be X units, and that is published in the newspaper, that will not really change the actual demand for the forecast, right? So this will have a very accurate forecast because all of these three factors can be satisfied. Looking at exchange rates, on the other hand, so we had three conditions, right? The first one is what are the factors that affect the forecast? In terms of foreign exchange rates, we don't really know like what all are the factors that are affecting it. I mean, it's a very complex model, even if we know it, even if we know certain parts of it. But just to put it simply, we don't really know. The second one is data availability. We have lots and lots of data, so that is satisfied. And the third one is whether the forecasts that we make, will that make any difference? And the answer is yes. Why? That's because say I forecast the US dollar currency to go up or go down tomorrow, right? For tomorrow, if it goes up, and I put that in the newspaper that the US dollar is going to change by this much, the market itself will shift by tomorrow. So my forecast will actually make a difference on tomorrow's forecast, on tomorrow's actual value, right? So that is where the relationship is not really independent. In terms of electricity, if I had made it public that this is going to be the forecast, there's going to be the demand, nothing would change. But in terms of exchange rates, everything would change. So this will be not a very accurate forecasting model. It can be compared to a 50-50 chance, like tossing a coin. So now I will go through some of the key definitions of forecasting. Looking at a point forecast, point forecasts are basically the mean of the possible future values that the random variable can take, right? So if I say that the electricity demand would be 100 units, that's a very specific forecast that I'm making. So that's a point forecast. The second one is the range of values that the random variable can take. So if I say that, I can't put a finger on it, it might be between 90 to 110 units. So that's a prediction interval that I'm giving. And the third one is forecast distribution. So what are the set of values that the variable can take along with the relative probabilities? So if I say that tomorrow's demand would be 95 units with um, 97% probability, maybe 98 units with 90% probability. So that kind of a forecast distribution can be made into for the random variable for tomorrow, right? So that's the forecast distribution. This chart depicts the total international visitors to Australia. So the blue line is what we talked about. It's the point forecast. The band, the darker blue band, is the 95% prediction interval, which you see is smaller than the lighter blue band. So the lighter blue band is actually the 80% prediction interval, and that's why it is higher. So as we lower the probability of the prediction interval, we are able to encompass more and more values. And then the last thing is there are two types of forecast. The first one is ex ante forecast, which is made using information available in advance. So standing today, I can use all the historical data and make a prediction, right? Uh, but in order to make a prediction, I will need to also know what the X variables would look like tomorrow. So I will need a forecast of the predictors as well. And this can be made through several different methods. The first one can be an averaging out. That is, I am averaging out all the historical data of the predictors and finding a value. The second one can be a naive prediction. It can just be basically today's value as tomorrow's value, the last observation. Seasonal naive would be an average of the last 2 years. So say sitting in May 2020, I can use 2018 and 2019 May and average it out. And a drift method, which is basically I can draw a straight line from the first data point that I have to the last one and then extrapolate it. So that's how I can do simple forecasting of the predictors. And this is the type of forecast which is most generally used in all the use cases. So because it is made using information already available, right? So it's the most feasible. The second kind of forecast is ex post forecast, which means after the event has occurred. So if I'm standing today, the forecast that I make for today itself, right? It's a look back forecast. So that's an ex post forecast because it's using later information of the predictors, which is already known. And this is helpful in understanding how the forecasting models are behaving, but it's not a genuine forecast as such. Okay. Now let's move on to understanding time series, right? What are time series? So this is another question. Which of the following is an example of a time series problem? The first one is estimating number of reservations in a hotel for next 8 months, estimating the total sales in next 4 years of an insurance company, or estimating stock market returns for the next 1 week. So you can paste your answers on the chat. Let me look. Is the question clear? Yeah. Okay. I got two answers so far. Okay. So majority of people have answered all, which is the correct answer. Why that is because all of these time series all of these questions have a time component to it, right? When we are estimating number of reservations in a hotel, we need the information at a weekly or a monthly level. So we need to make a time-based forecast. Even for the second one, the total sales prediction for the next 4 years, we need to make a time-based forecast, and even for the third one. So a time series is basically just a sequence of observations that we record at regular time intervals. It can be hourly, daily, monthly, quarterly, annually, and so on. So that's the simplest definition of a time series. What are the components of a time series? So the first one is level, looking at the mean value of the time series, that is the level of the time series. The trend, which is the long-term increase or decrease in the data. So we can just say that whether it's an upward trend or a downward trend. The third one is a seasonal pattern, right? So seasonality is basically a fixed and unique repeating frequency pattern. So it should be a repetition, but that repetition should be fixed. I mean, it should be regular and it should be known. And this can be like a day of week seasonal pattern. It can be a monthly seasonal pattern. It can be annually, once in 2 years, and so on. Now, seasonality is different from cyclicity. So cyclicity is basically rises and falls, similar to seasonality, but they are not fixed. They can be long or short. In terms of the first, say, cyclicity was about 6 years. The second one can be about 10 years. The third one can be about 9 years, right? So that pattern is not of a fixed period. And then we have noise. So in any time series, I think if we didn't have noise, it will become deterministic. So there's definitely a noise component, and that's a random variation in the series, which is why this branch of statistics is there, right? To study what is the best way to forecast a time series. So on the left hand side, this is a trend only time series. There is no noise. I mean, we can't see any variation, right? We can't see any seasonality. There is no cyclicity as such. The second one is a seasonality only. So all we can see is a seasonality. There's no trend, because if we look at from 1870 to 1995, we are not seeing an upward or a downward trend. And the third one is a trend and seasonality. So the pattern is repeating, but the overall, there is an overall increase in the value over time. Can you identify the patterns that are present in these time series? So the patterns that we talked about mainly are trend, seasonality, and cyclicity. So you can just mention in the chat which of these three are present in this particular series. Okay, I've got two answers for cyclicity. Yeah, cyclicity is present. Anything else? Okay, I think this one might be a little hard to find out. Yeah, perfect. We have cyclicity and seasonality present. So there is an yearly seasonality as well that we can see in the time series, right? It's going up and down at a yearly level, but overall overall there is a cyclic pattern, which is not really constant. It's between 6 to 10 years. How about this one? Perfect. Yeah, we have trend and we have noise in this series because it's not a perfect downward trend, right? Okay. I have not mentioned noise here because it's understood that any real life time series will have noise. So just mention trend. How about this one? If you have gotten the past two, I think this would be pretty easy. Perfect. So got an answer from Zinc and Arka. Trend, seasonality should be present. Yeah, and Tuhin. Okay, that's perfect. And how about this one? Okay. Yeah. Shichao has given the right answer. This is just noise. Seasonality is not really present because uh, although it looks like going up and down, we can't really see a very distinct pattern, right? So remember, seasonality should be a fixed pattern. The magnitude of this seasonality should also be constant, right? If we are only looking at a pure seasonal component. So pure seasonality will have a definite magnitude. It should not increase or decrease. Um, we can eyeball it. Okay. So it's just noise. Now so far we have looked at the different components of a time series, right? And this is mainly through a visual perspective, what is happening. Now let's go a little bit more into it and look at autocorrelation and partial autocorrelation. So correlation is a measure of a linear dependence in a time series, right? Um, so the main keyword here is linear. We can see all at the bottom of this chart, there are different um, types of data, right? So they're all spatially scattered in different patterns. But if we just look at the Pearson's correlation, all of these are zero correlation values, right? Because they don't have a linear dependence. There is no linearity in this data. So that's why it's a zero correlation. On the top, you might already know this, but just going over it very quickly. A perfect one correlation is the highest correlation that there can be. This is a straight line. Now, remember, correlation is just about the linearity. So the slope of this line, if you plot it, doesn't really matter. It can be a slope of 0.3, it can be a slope of 0.5, it can be anything. It just has to be a perfect line. The second one is 0.8, right? So we can see data points are scattered a little bit more. 0.4, a little bit more scatter is there, but we can see that there is a trend. 0, we can't really see anything, right? Minus 0.4, again, we can't really see anything. I mean, we can see it's a downward trend, right? Minus 0.8, again, the scatter is lessening. So it's a stronger correlation, but it's a negative correlation. And -1 is again a perfect line. The second actually row is a little misleading, but it's just saying what I said earlier. The slope doesn't really matter. So there are different slopes, but as long as there is any kind of a slope value, if it is a positive slope value and it's a perfect line, the correlation is 1. If there is a negative slope value and it's a perfect line, it's a correlation of -1. So this is what correlation is about. Autocorrelation is nothing but looking at the correlation of a value at time t and of a value at time t plus h. So correlation is just covariance divided by the multiplication of the different standard deviations. And this is how the autocovariance is defined in terms of the expectations. Partial autocorrelation is nothing but if we have an autoregression equation, right? So y at time t, how it can be regressed from all the observations prior to time t. So alpha 0 is a constant plus alpha 1, y t minus 1, and so on. So if I were to say what is the partial autocorrelation for lag 2, then alpha 2 would just be that value because that's the coefficient of yt minus 2 in this equation. So that's pretty much what partial autocorrelation is. Another fundamental concept is stationarity, right? So a time series is stationary if it follows three conditions. The first one is if it has a constant mean, it should have a constant variance, and the autocovariance or the autocorrelation that we just looked at, it should only be dependent on the lag. So if you're looking at xt and xt plus h, no matter what t is, right? If our h is the same, if the lag is the same that we are looking at, the autocovariance should remain the same. So if these three conditions are satisfied, a time series is stationary. In simple words, it should not be a function of time. So white noise, for example, is a stationary time series. Why do we care about stationarity, right? Forecasting is easier for a stationary time series, and forecasts are more reliable. And also, if you remember, we just looked at an autoregression equation. So autoregression equation is just a linear regression equation, but for a time series. And for linear regression, we should not have any sort of a relationship between the different x variables. So the x variables should be independent. If there is a relationship between the x variables, then the assumptions of linear regression don't hold. So that's why to enable that independence, we need a stationary time series in order to build an autoregression model. Let's look at stationary time series. So based on what we just saw, is this a stationary time series? What do you think? So you can start by identifying the patterns. What are the patterns? And then look at the definition, right? Remember, I just said that noise is kind of a stationary time series. So does this one look similar to noise or not? Or does it have any kind of a pattern in it? Okay. Okay. So there are a couple of answers. They are going up and down between non-stationary and stationary. Let me see how many have said stationary. Okay, I think we have two answers from stationary and or three answers for stationary and two answers for non-stationary. Okay, this is actually having a very strong seasonal component, right? If you see, there are very consistent dips in the data, right? So since this has a seasonal component, it is not stationary. Just by eyeballing it, I mean, this is the one way that we can say that this is a non-stationary time series. Otherwise, we need to actually do a test and then find out. How about this one? Remember, there were three conditions. The first one is constant mean. The second one is constant variance. And the third one is that the autocovariance should only be dependent on the lag. So it should be independent of the time t. Okay. Any other answers? Four answers for stationary. So when we talk about variance, right? What is variance? It's the spread of the data, right? So if we look at the spread of the data prior to 1995, we can see that it's between, let's say, about 800 units to negative 1,000 units, just 1 point going below 1,000, right? That's prior to 1995. But if we look at 2005 onwards to 2010, we can see more spikes, right? There is a higher spread of the data. So the data is actually moving up and down very, very, I mean, frequently and strongly. So the variance of the data has increased post 2005. That's a fair statement that we can make. So looking at the series, since uh, the variance is not the same, right? Or like in technical terms, we can call it heteroscedasticity. So homoscedasticity is constant variance, and hetero, right? The word hetero means different. So this is a non-constant variance. So this time series is non-stationary. Let's look at a last one. How about this one? So for this one, you can disregard the variance, right? Right. Left hand side might seem to be right. There is an answer by Sani, constant mean, relatively constant variance. And yeah, that's the right answer. Right. So this is a stationary time series. Because the mean is constant, it's a straight line. And that's pretty easy to see, but even the variance is sort of the same. We can see spikes, but it is same. So in case the series is not stationary, right? If it does have kind of a seasonality, kind of a non-stationary, non-constant mean or non-constant variance, how to make it stationary? So there are two ways, right? If we have a seasonal time series, we first seasonally difference it so that the seasonality is removed, and there can be multiple seasonalities in the time series. It's not necessary to have just one. So in that case, we need to do multiple differences, seasonal differences. And the number of seasonal differences to be done, it's very beautifully captured in an R package, nsdiffs, that is the function name. This just gives the number of seasonal differences to be made. Once we have done the seasonal differences, then we can go on to the next step, right? If the series is already not seasonal, maybe there is just a trend in it, then we directly go to the next step. And the next step is just to difference with successive data points, right? So if there is a trend, differencing with successive data points will make it stationary, will remove the trend in it. And the number of differencing that we need to do is again given by n-diffs. That is again an R function. So when we are modeling, for example, and we are given a data that has a good seasonality and it is not stationary, like for example, the first one, it's not stationary, right? The seasonality, we need to difference it out to make it a stationary time series, model for it, do the prediction, and then add the seasonal component back into it. So that's how we will model for the stationary time series, but also add back the component that we have removed using this differencing. So that's how we can incorporate stationarity into our forecasting. So far we looked at time series. We mainly understood what does stationarity mean, what does correlation mean. So this was more of a very traditional statistical method and understanding. Now we will go a little bit more into the machine learning side. Where does it come in? And how do we actually frame a time series problem as a machine learning problem? Machine learning, there are mainly two use cases that are the most popular. One is classification, one is regression. And where does time series actually fit into it? So time series actually can be framed as a regression problem, and we will just see how. Before we go into that, the first step, right? It all starts with data. The first step that we need to do is do data pre-processing. And there are two things, two major pillars there. The first one is imputation, which is basically filling in the missing values. And the second one is outlier treatment. I generally use R, right? There are a lot of other options in Python as well. In R, there is an impute TS package, which has about 10 different imputation methods. So uh, other than the mean, median, mode, the three kinds of imputation, we also have a very sophisticated imputation techniques. Some of these are like using structural model and Kalman smoothing. So that's a pretty popular one that I have used in the past. And also using exponential weighted moving average. So it depends on the data that we are seeing. If exponential models are fitting very well, and if the most recent value is the most important, then we can use an exponential weighted moving average. So imputation is the first step to do if we have missing values in the data. And also we need to do outlier treatment. So if there are outliers, it might, add noise to our model. So we need to feed the model very good quality data and feed in something that it can learn from very easily. So that's why we need to remove the outliers when we are training the model. There are 5 major different kinds of outliers that have been identified in a paper by I think in a paper in 1993. Uh, that was a major study done on outliers. First one is additive outliers. So it's just an isolated spike. Just 1 month or one data step, the spike occurred. Then there is a level shift. There was an abrupt change in the mean level. For example, due to COVID, if we see the sales of a particular product, it definitely would have seen a very abrupt change in its level, mean level. So level is just the mean value of the particular say of the sales. So there is a level shift, and that's an outlier. The third one is temporary changes. So spikes, like similar to additive outliers, but they disappear after a few periods. It's not a instant disappearance. It's after a few periods. Then there are innovative outliers, also known as intervention outliers. So these are something which are more difficult to explain in easy terms. So I'll just skip this. But just for reference, I've added what does innovation mean. So innovation means that say at time t, I'm observing a certain value, and that is say 10 units. That's the actual value of that variable, and it's 10. Using all the historical data up to time t, if I predict what should be the value at time t, and that comes out to be say 20. So I'm actually expecting 20 units for time t using my model, but the actual value comes out to be 10. Then that's an innovation. That's an innovation outlier, because it's something very different from what I'm expecting. Right. And this is again something in the case of COVID, which we can see in different variables, like in the sales, in say number of travel, like trips done by people. There can be multiple different things. Everything was disturbed, right? So that's again an innovative outlier. Uh, Level shift can also like come under COVID, but I mean, COVID was a complete different universe, right? Everything changed. So uh, we can't really classify it here. The last one is seasonal level shifts, which means an abrupt seasonal change in the mean level. So it's similar to a level shift, but including seasonality. Okay, let me come now to the most important part. I mean, this is the core of machine learning. Like if I had to classify, I would say that data is about 30%. Feature engineering is the major part. I mean, it's 40 to 50%, and then modeling and so on. Right? Why it is important is because the data that we have, it's not really visible what all information it contains. So our job as either a machine learning engineer or as a data scientist is to get that information out of the data, make it very explicit to the model that this is the information present, and then ask it to learn from it, right? For example, if we have timestamps, we need to extract what day of the week it was, whether it was a holiday or not, which year was it? Was it a leap year or not? Um, was the, I mean, other um, time related features can be extracted out from it, and that is useful information. If we discard that, then all that information will stay lost. And uh, if that information is very crucial for the model to learn, then it will be missing out on something, right? So for time series problem, we need to explicitly create time related features. And these are all available in Python's timestamp and datetime index attributes. So we can extract year, month, day of week, quarter start, and so on. So we are adding new columns here, right? That's what I mean by features. We are just taking the existing data and adding new columns by extracting information from the existing data. So here I just looked at time, just the timestamp. The second one is looking at the predictors. Um, we want to see if there is a lag relationship. So what I do now, right? If I say invest or give an incentive of certain units to a customer, will that affect a future customer coming in 3 months from now? So my current incentive, will that in any way affect, say, 3 months from now sales? Another example can be advertising. If I advertise now, if I give you a TV or a radio advertisement, there is expected to be a lag. So customers would see it and absorb it, and then maybe 1 month or 2 months later they will come in and check the product out, and then maybe even buy it. So there is definitely a lag relationship of predictors with the target in many cases. And we can find out this particular lag by looking at a cross correlogram. So looking at the lags of the predictor versus the target, lag one of the predictor versus target, and so on. Another kind of a feature that we can add into our data set can be a rolling window feature. So here we can define a window size. We can take different kinds of window sizes. That can be one, you can call it hyperparameter, right? For feature engineering that we can take, or one parameter. The second one can be what kind of an aggregation do we want to make. We can sum up the values, we can take the minimum, we can take the maximum, we can do a weighted average as well, depending on if it's, say, the most recent observation is important, then an exponentially weighted average will be best. And that can be a new feature which we can add. Rolling window means that the start is changing each time. In each iteration, the window size is fixed. And similar to it, there is expanding window where the start is fixed. The window size is changing each time. So window size is expanding, and we can do the same operations. And then depending on the domain in which the problem lies and what we are trying to solve, we can have domain specific features. So recently a package called TS Fresh was published, and it has a very good capability of feature engineering. So you can check it out. I've shortened the link and it's here. It has about, I think, hundreds of feature engineering for time series. And it's looking at different window sizes and extracting information such as, I think, Fourier decomposition, a lot of different features. So you can check this out. So once we do feature engineering, the next step is exploratory data analysis, which in simple words means looking at the data, visualizing it to see if there are any major trends or any outliers, etc. So typically outlier analysis can be done in this phase as well, right? Looking at all the different outliers, but imputation is something which should be done at the start of the EDA. So because we should first plot the data, look at the missing data, and then impute it, and then again plot it to see whether that imputation makes any sense, or is there something wrong with it? Are we imputing for an outlier? So all that kind of scenarios. This first plot is a line plot. This is the simplest kind of a chart, although this is a 2-axis line plot. On the first y-axis, we have personal savings rate, and on the second y-axis, we have unemployed numbers. So this is the first kind of a chart that we can create. The second one, which I have listed here, I mean, there are multiple charts that can be created. This is a stacked line chart. So we are looking at night visitors in Australian regions. by values, right? So there is a very clear pattern here. Different regions have different mean values, so it's very good and easy to visualize it. This one on the bottom left is about the trend and seasonality using box plots. So the first one is an year-wise box plot. What we are doing here is we are looking at an year. So basically we have 12 data points if the data is monthly, or if the data is daily, we have 365 data points in a particular year. And then we are drawing a box plot, right? So looking at this over time, we can see if there is a trend or not. So in the box plot, we can see the median values, and also we can see the outliers and the interquartile range. Opposed to this, we have the seasonality plot, which is a month-wise box plot. So this can be month-wise, or it can be a day-wise, it can be hour-wise, so on. So it totally depends on the data that we have. This is assuming monthly data, so that's why we have 12 different box and whisker plots, and this shows the seasonality. And the last one on the bottom right is another great way to visualize the monthly stock prices or the monthly data, and use color coding for it, right, to show the values. So there are different charts, and this one was published on Machine Learning Plus. It contains about top 50 matplotlib visualizations. So there are multiple other charts which can be used, but generally matplotlib, seaborn, plotly, these are some of the main tools used in Python we use, and in our ggplot2 is the main one. I mean, I've worked with both. So I find Python to be little easier on the plotting. R is very custom. So if you know R very well, then you can really go into ggplot. But for a beginner, I think Python is the best. Okay. Now let's jump into machine learning, right? So far we have looked at the data, we have engineered features, we have looked at the plots, understood the relationships. Now we are ready to build a model. So what does a machine learning life cycle look like? There are three main components to it. The first one is data, and that's the starting place, right? Then we have a model, and then we have the code. And model and codes, I mean, they work in conjunction, so they work together. But the reason why it's shown differently here, so that we can understand the flow better. So we start with the training code, where we write our scripts, and we have the training data already available. So we data into training and test, training, validation, and test, right? Before we do any kind of a modeling activity. So a typical split is about 60, 20, 20. So 60% for the training, 20% for validation, and 20% for test, or it can be an 80, 10, 10 as well. Once the model is trained, it should be validated, right? Validation mainly means so I have created a recipe from my data, right? When you're cooking, you can relate to it. You have created a recipe in, say, you have written it down. I should take this much amount of a particular ingredient, but then you want to test it. So you go ahead and test it in your own kitchen first, right? That's the validation set. You test it and see how it is performing. If it is performing well, then that recipe is good to go, right? And you can show it, or you can serve it to visitors. If it is not good, then you will again go back and revise your recipe. So that's where you will go back and retrain your model. You will see what went wrong, why it is not performing well on the validation set, and so on. So that's where validation set comes in. The test set should be completely unseen data. So something like a visitor who is coming to see your house, you serve the recipe once to him, right? And he goes away, he goes back, I mean, and there's a very less likelihood for him to come again and eat the same dish from your hand. So it's kind of a one-time activity. So a test set should never be used twice. If you use a test set twice, if you see what was his feedback on your recipe, right, So he will have a certain feedback. You can overfit your recipe to suit that person. Maybe he has a spicy taste. If he's saying that the taste is less spicy, you can make it more spicy. But say you have another visitor who comes in and who likes more sweet food, that recipe will not suit him. So it needs to suit all kinds of people. I mean, I'm talking in a very general sense. So that's where the test set should never be reused, and that's very important for machine learning. So training and validation and test, these are the three kinds of data that we need to split before starting modeling. So there's the model building activity that we start with. Then we do model evaluation and experimentation. So here we have the validation data. This is mentioned as test data. We can keep it as validation data, right? We are evaluating the model and on certain metrics. And based on that, we are choosing a model, right? So we choose a model. If it performs well on the test, on the validation data in the first go, we can directly choose it. Otherwise, we go back into the model building activity and again evaluate and experiment. Once we have the chosen model, now what we do is we train on all the data that we have, right? So we train on all the data. Here, actually, we only have training and validation. So the split can be something about 80 and 20. We are not looking at test here. So in this case, we have 80% training data, 20% validation data, and we are choosing a model. We are productionizing that model using 100% of the data. We are training the model, right? We have productionized it, means we have maybe made it a pickle file, or we have dockerized it and so on. So it needs to fit in into the deployment pipeline. And then we are testing it. So for testing, we need test data and test code. It's giving out a model, right? So here again, there are metrics. We get a model, we get a final model, right? This is unseen data. So this is like, a friend who is coming to your house, you want to test it on him before you actually serve that recipe in a proper restaurant to, strangers. So that's kind of a test that we are doing here, right? We have a final model and then we deploy it using application code, and we have the code and model in production. And then we are monitoring the model's performance using the production data. So when new data comes in, how is the model actually performing? Based on this observation and monitoring, we go back into the model building phase. So this is an iterative activity. If the model is not performing well on production data, and it performed well on the training and the validation and the test data that we served it, that means there is a training serving skew. That's what it popularly called. That means the data or the model that was performing well in production, it is not performing well now. That can be for a couple of reasons. I'll go over that later. So this is the machine learning life cycle, right? Now where we are standing at is the model building. So let me go over some of the algorithms that we use for time series. ARIMA is the most, easy to use and the most well-known statistical algorithm. It's a very powerful algorithm as well. But Facebook has also released Profit library, and it is a strong contender for ARIMA. I mean, in several ways, it performs better than ARIMA. We have Holt Winders, which is exponential smoothing method. There is BATS and TBATS. These are available as functions in R, but not in Python so far, right? So these can model for complex seasonalities, right? If seasonality is very complex, it's not simple. These can model for that. Then we have spline functions. If you have used cubic splines for extrapolation, you can refer to, you can understand spline functions. There are theta models, which are again sophisticated models. This is available in the R library as a theta function. Then we have STL decomposition, seasonal and trend decomposition. neural network autoregression, right? And this is also present in R and in Python. We have multi-seasonal time series, Bayesian structural time series, and dynamic harmonic regression. So all of these are actually univariate time series, which means that we are only using values of the target variable in order to forecast it. We are not using any other explanatory variable. For machine learning, however, explanatory variables is where all the fun begins, right? I want to be able to correlate different things and basically make my model more intelligent, right? So that's why we generally frame the time series problem as a machine learning regression problem. So that's why we have a lot of regression methods that can be used. We have linear regression, lasso regression, ridge regression, which are generalized linear regressions, elastic net regression, random forest, which is a bagging method, gradient boosting, adaptive boosting, and so on. And we also have generalized additive models. So this is another very good set of models that can be built. The reason why I like this particular set of models is it's easy to explain to whoever is using your predictions, because we can use the partial dependence data. So we can draw a partial dependence plot and show how a variable is affecting the target. In other methods, it's mostly black box. So random forest, if you use, you can show the feature importance, but other than that, you can't really, it's not easy to explain. And there are a lot of complexities which are there inherent to it. And GAMs, on the other hand, are simple. But the state of the art is neither statistical nor machine learning, right? It's a combination of both. That's where ensemble-based models come in. What we do here is we take predictions of the statistical models, we take predictions of the machine learning models, right? And create a data set out of it. Basically, from these predictions, on top of them, we build another model, right? So we have model one, model two, all of these predictions coming in, and we build another stacking model, which on top of these predictions predicts the final output. So say my actual value for sales was 10 units. Model 1 predicted 8 units, Model 2 predicted 9 units, Model 3 predicted 8 units, Model 4 predicted 7, and so on. I will not take the explanatory variables. I will not take what is affecting the sales. I will only take these prediction values, build a model to say that, having these as inputs, the target should be 10, and that will be my second layer model, the stacked model. So this is an ensemble based model which performs best for time series problems. My recommendation would be to check out two main libraries. One is Python's Neural Prophet, which has been released by Facebook last year, right? It combines, it uses PyTorch, so it combines neural networks and Prophet. It is a very powerful library. And the second one is the tidy models in R. So what tidy models has done is end-to-end all the data preparation using tidyr, plier, dplyr. All of those are included in this particular series of package. So this package has a lot of different functions and libraries. Now, I also want to talk about M competition methods, right? So Makri-Dakis competitions they evaluate the state of the art forecasting accuracies and methods. The last one was held in 2018. It had about 0.1 million time series at different frequencies. And the objective was to find out the algorithms which predict the best for these time series. There were certain benchmarks for the point forecasts, right? Point forecast is just that particular value. So these are some of the methods. The naive approach is the random walk model, which is just taking the last known observation. This is a benchmark against which to see the new model, the new algorithm. The second one is a naive seasonal, which is just looking at observation of the same period. So if it's a month of May, looking at last year's May. Right? And we have exponential smoothing, we have Holt, we have theta, we have a combination of all of the three, that is exponential smoothing, Holt, and damped exponential. So this is good as a reference. um, if you're building any new time series model, make sure that you're looking at these benchmarks and making sure that your model is performing better than these. Okay. Coming to model evaluation, right? So we have looked at algorithms, but we also want to have a very fair evaluation, because remember, machine learning is all about finding patterns and generalizing well. So the generalizability comes through a good model evaluation. If we are overfitting the data, then in the future, what we are predicting will definitely have a very high error. So we need to make sure that the model that we have built is very generalizable. And this is where backtesting comes in. So this is similar to a general cross-validation approach, but here we are looking only forward in time. We are not taking future data and trying to predict the past, right? In a regression problem, if you see, we don't have a time component, right? So that's why through different iterations, we can jumble the data as we want and then create the different sets, the train and the validation. But for time series, since there's a time component, we need to move sequentially. So this is a sliding window approach in which the window is constant, right? We are dropping the earlier data, and here we are predicting 4 months ahead or 4 data points ahead, right? So this is the forecast horizon, n+4. On the other hand, in an expanding window, the start point is the same, and then we are again training, we are predicting for the red point. In pass 2, we are again training on one additional point and predicting for another data point, and so on. Right? So which of these should we use? The argument for sliding window is that older data, it's not really reflecting the current reality. If there is a lot of drift in the concepts over time, right? If the strategies have changed or if the conditions have changed significantly, right? It makes sense to use the most recent data, because that will help us reduce the noise that the model is learning. But if there is no such thing, I mean, if the data is very strong from the start, we can use an expanding window. The more the data, right, the more the fuel, the more the oil, the better the longer the car will run. But in this case, I mean, the better the model will be. Okay. In scikit-learn, we have time series split. So that's a function which we can use for this kind of an approach. Now, we looked at the approach, right? We looked at how to do it, but what are we actually going to measure? Is it going to be just the simple error or the absolute error, right? There are scale dependent errors. So there is a mean absolute error, which we are just looking at the absolute error and taking the average of it. Then there is the root mean squared error, right? Which I think most of us would be familiar with, RMSE. But these are all scale dependent. If the data, say, is in range of millions, then the errors will also naturally be in terms of millions, right? Maybe 0.1 million, but still in millions. On the other hand, percentage errors remove the scale, right, by taking a percentage. So MAPE is one of the most popular percentage errors. It's just taking the percentage of that error for that time step and taking the mean of all the different percentages. Then we have scaled errors, right? So this is a very big equation that you see here. I'll not go over it in much detail, but it's just taking the, if you take m as 1, right? If m is equal to 1, what it is actually doing on the denominator, it's taking the error of the random walk model. So random walk model takes the current data point and the last data point, right? It uses the same error. It uses the same observation. So yt minus 1, it's taking the successive predictions or successive observations error and averaging it out, right? So basically what this is saying is, if our model is better, if our model's error is lower than this random walk model, then MASE will be less than 1. If our error is greater than the random walk model, then MASE will be more than 1, right? So it is a mean absolute scaled error. And then we have direction. So the first three are very well documented, but direction is something which, working with time series over time, I think uh, I've found it to be very important when explaining, the effectiveness of the model. What direction says is, are we predicting in the same direction, right? If we, with respect to the current steps actual data, the next steps prediction should be in the direction of the actual data. So say currently it is 10 units. Next month, the actual is going to be 8 units, right? If I've predicted 9 units, I'm good to go, right? Because current is 10, I have predicted 9, and actual was actually 8, will be actually 8. So I'm in the correct direction. What is not included here, it doesn't include what I actually predicted for the current month. Say I predicted only 7 units for the current month, and it is 10 units. Next month it is going to be 8 units, and I predict 7.5, right? Am I in this right direction or not? So it should be in the same direction as the actual data. I mean, if I'm moving uh, down, then that means the direction is right. So if I move from 7 to uh, 6.9, it means I'm capturing the seasonality. So it is a very subjective measure. So this is another measure that we can use. Finally, building a model is good. Evaluating it is also good. But the challenge in machine learning comes when we need to explain the model. We need to explain, say, why it is predicting and be able to trust it. So that's where there is a library called SHAP. It works for any kind of a model, right? It doesn't need to be any machine learning model. I mean, it doesn't need to be a tree-based model or a regression model. It can be any model. It is model agnostic. What it does is, let's take this example and assume it to be a tree-based model, right? Uh, LSTAT stands for lower status, and we are trying to predict the home prices here. So basically saying, how does status affect the home prices in a particular region, right? So the red points are showing the actual data. So for LSTAT, we have a lot of red values and a lot of blue values, right? Um, so basically on the x-axis is the SHAP value, the impact, that is kind of similar to a feature importance. So LSTAT seems to have the highest importance, right? When it is red, the SHAP value is negative. That means it is a negative correlation. If the SHAP value is blue, right, and it is towards the right, then it means that a lower value of LSTAT, a lower status, will have a higher impact, positive impact, higher positive impact. So it's a negative correlation. But in addition to negative correlation, it is also a very strong correlation or strong importance, actually. So this is what a summary plot of SHAP will look like. This can be done for any model. And this is on a very high level, the left-hand side. The right-hand side is saying for a particular prediction, why did it predict what it predicted, right? So if we make a prediction, we can actually explain using this why, how the different factors are affecting that prediction. So for example, on the bottom, you can see expectation of f of x, right? Expectation of y basically is minus 2.685. This is looking at the average of the historical y values. If I have 30 data points, I'm just taking the target average over the 30 points and coming up with minus 2.6. Now what I'm saying is, from this average, the values of the month that I'm trying to predict, right, they are causing the prediction to vary in such a way. So occupation, for example, it's causing minus 0.11 change, right? It's making it negative, this average value. Capital loss of that month is again pushing it towards the lower bound. minus, right? Education num is pushing it towards the positive, right? 0.4. Marital status is pushing it towards negative, and so on. So here we can see the final value that we have come up with is minus 5.88. This can be a random forest output, right? It can be a prediction. And this particular chart can show that just a naive forecast would be minus 2.6. But since we use all of these different x variables, this is the value and this is how we have arrived at it. So this is very useful to explain the model. The last thing is about model deployment. So we have built a model, we have evaluated it, we have explained it as well. And now we finally want to deploy it. In deployment, we are also considering we need to monitor it for a long time so that the model becomes stable. And I think this is where, the most care needs to come in, because in industry generally proof of concepts are very, a lot of proof of concepts are done, but to deploy a model, there are certain complexities which need to be taken care of. So the first one is model refresh. This is one question that we need to answer is, when should we actually refresh a model? Like I built a model and I've deployed it. Do I need to change it or not? A general benchmark is about a quarter. So we keep the model for 3 months in production, observe its performance, and then based on that, either continue with it or refresh it. The second question is, while we refresh it, should we use the same features and the hyperparameters and just update the new data points, or should we change the model? So this is to see whether the model that we built, is it still holding good or not? If it is holding good, then we can just update with the new data, right? If the previous model that we had built earlier doesn't need any change, it is already performing at a 95% accuracy, right, at a very good accuracy, then we will not do anything. We will not even update it with the new data if we find that after updating with the new data the model is deteriorating, right? So we need to monitor the model refresh very carefully. Only if it is essential we should do the model refresh, and if the new data is improving the model, only then, right? The second one is model monitoring. So there are three things. One is the data drift. Have the statistical properties of the input data changed, right? The say incentives that we were giving for a particular sales, for a particular product sales, have they changed very significantly? So have the statistical properties in the distribution changed or not? The second one is concept drift. Has our sales itself changed or not? Has a new competitor entered into the market? So that will change our predictions. So we need to tune the models then and go back and tune it. And the third one is model drift. So model drift is basically looking at the model coefficients, whatever updates with the new data that we are making, how are the coefficients changing? So the relationships should remain the same. So that's the ideal thing. But if the relationships are changing, then we have a model drift and we might need to make a new model. So that's where the model refresh will come in. On the tech stack, I think there are four main things. We are not really software engineers, so we will not know everything about packaging it and deploying it. But for a data scientist, I think Docker is the main tech stack that we should know. Basically, we will be containerizing the application, which is the data pipeline that automatically transforms the data, the machine learning pipeline that can take the data, do the automatic feature engineering, automatic model building and evaluation, and then decide whether or not to refresh and so on. So that application should be put in a Docker, right? So we should know how to Dockerize it. The second one is when it's in production, right? We also want to tune the models. We want to observe and monitor the models. So in production, generally, we will not be able to use our local systems. We will not be able to, get the data from a production environment. Say, Facebook is or Amazon is running its recommendation engine, and we want to find out if there is a data drift or if there is a model drift, right? The data and everything is stored in a production environment. So we need to do something on the production environment itself, right? Pull the data and experiment with model building. So Amazon SageMaker Studio enables that. So this is another very good, I think, AWS service that you can look at. The third one is Flask, right? It's very simple to use. It's basically we are creating an API of our model. So when the front end, say we are using a mobile app, we hit in a query, right? And that query goes back and hits our model to basically say, if the user has this query, what should be the output? So that process uses an application programming interface, that API, and we can expose the API using Flask, right? It's very simple to use. We can put the model into integrated Flask and serve it as an API. And for API testing, we can use Postman, right? So this is something I think which is very simple. I mean, it's not used, but it's just for testing. Okay. The last part of my talk, I have a tutorial on deep learning with TensorFlow. So for those of you who want to, get into deep learning or are already in deep learning, how do you actually proceed with time series, right? So for time series, we used recurrent neural networks. Let me dive deep into it. So Johnny, how are we doing on time? Do we have, say, 10 minutes?
I think you could cut short on this one.
Okay, sure.
Maybe you could go very briefly for this one, maybe 3 minutes. I mean,
okay.
Then we can let the audience interact with you a little bit.
Okay, sure. Is my screen visible?
Yes.
Okay. So for time series, I think recurrent neural networks are the most popular, right? So how they look like, the basic concept behind it is, in a traditional neural network, there is no parameter sharing. So a lot of different parameters are there for different neurons, but in a recurrent neural network, the parameters are shared, right? So there is a recurrence which is occurring, which you can see on the right hand side, right? But RNNs also have a recurrent hidden state whose activation at each time depends on the previous time. So it's really a very time dependent or a sequence dependent architecture, right? That's why it works very well for language NLP use cases. If we unfold a recurrent neuron, that's how it looks like, right? We are unfolding it through time. So the parameters are shared. You can see U, W, V. That is the same parameter over the neural network, throughout the neural network. Right? So that's why the parameter sharing, and the input is flowing and into and out, right? We have an output at each step, which is OT, and a hidden state, which is sent forward, right? So ST is the state. Okay. I'll not go over the use cases. I think it's not really relevant for time series. Okay. So some of the key terminologies, we have epoch, which is a complete pass through the entire training data set, batch size and steps per epoch, right? Let me skip over this as well. Okay. Coming directly to the case study. So here we are considering a time series of 9900 days from M4 competition, right? And we have imported, we are using TensorFlow 2.3, Pandas 0.25. The data is available on this particular GitHub link. right? It's under M competitions, github.com. So I've just downloaded the data, and there is both train and test data, right? So this is how our data looks like, right? The features are D1, D2, so on, and the labels of the rows are V, V2, V3, and so on. And this is how the test data looks like. So the train and the test data, I mean, have the same number of columns. So now, actually, all of these are different time series. Now I'm just subsetting for the longest time series, and this is how it looks like, right? So you can see there is a sudden dip after 2038, maybe. So I've actually removed that, right, for my model building purpose. And now I will split it into a training and a validation set. So before doing so, yeah, I have split it here into a training and a test set. And the horizon that I used for this, I think, was 14 days, because we need to predict for 14 days. First step is to check for stationarity. So we can use the augmented Dickey Fuller test here, which is a unit test, unit root test. So the p-value is very, very small, right? So that's why we reject the null hypothesis and say that the time series is actually stationary. So we are all good to go, right? The reason, we are rejecting the null hypothesis is because this test says whether there's a unit root or not. If there is no unit root, that means this time series is stationary. Very simple feature engineering, just creating a day of week and month, right? And doing some data pre-processing. So just want to show two objects, right? One is the time series generator object, right? This can be used to actually create the pipeline that RNNs require. And the second one is the different functions, right? The callback functions. So we can create checkpoints to see how our model is actually performing, and early stop it if the performance is deteriorating over time, right? We also have reduced learning rate on plateau and so on. So here I've trained LSTM models with this architecture, right? Just two layers are there, one LSTM layer and one is a dense layer. And this is how it looks like. You can see that the data has been embedded into a certain dimension, 20. And the output is again 32 for the first layer. That is the dimension. And the output is 14 because we need a 14-day forecast. Right? So here I fit the model. And see, you can see that validation loss is improving from infinity to 0.02. It is improving, but at a certain point, it is not improving. So if it doesn't improve once, then the learning rate decreases. So by reducing the learning rate, we are basically converging to the lowest cost function, lowest loss, right? The cost function, since we are going down on the cost function, we are reducing the learning rate so that we are able to converge more quickly. So that's what we are seeing here. And finally, there is early stopping done because it's not improving for 3 iterations. Similarly, if we drop out, we can create a neural network architecture and continue the same process. Another one is a stacked LSTM model that we can use. So we are basically using different layers of 3 layers of LSTM networks. Again, we can do this one with dropout. So a lot of different experiments that we can make here. Then we have stateful models. So it preserves the state from the past run, right? Okay. So let me just go directly to the summary. The results were measured. So the actual evaluation metric was SMAPE, which is symmetric mean absolute percentage error, right? It's similar to MAPE, but the symmetricity is also baked in. And these models had about 1,000 units of mean absolute error RMSE was also about 1,000, right? MAPE was pretty high, right? 2797 was the SMAPE. So there is, if you see the time series, there are certain trends and seasonality in this time series, which is the next step. We should be differencing for the seasonality to make it. So we have the time series is also already stationary, but there are more operations on the pre-processing that we can do, right, to make the model better. So that's what we can take out, from the results. Yep, I think that is all I had from my presentation. If you have any questions, I think we can open up the forum. For connecting with me, you can reach out to me on LinkedIn or through email, and I'm happy to connect. Thank you.
Thank you very much, Anant, for sharing. And it's quite a good talk. And it's actually a very good lecture and tutorial too. So do you have any question from the audience?
So one question I have is, how how much are you using machine learning right now? I understand this is a geochemistry data mining project. So, what are the difficulties that you face using machine learning? I mean, if you're stuck at any place, which is the one area that you feel that needs more development from the machine learning community?
For myself, for the project that are going on, I don't think that the machine learning tools we have problems for that because it's quite a mature tools that we have been using. I said people are getting more familiar with these tools and solve this problem. To me, I think the bigger problem that in the future that we should face is to trying to find the new algorithms that we didn't know or it even didn't exist in the market. So, but I think it will still take some time before we could make a more specific request, what type of new algorithm that are needed.
Right.
So far we're still in the learning process. For example, for some projects that they need to find some feature importance of certain elements uh, for the different minerals. And so we are learning the XGBoost or LBGM, for example. And yeah, but those are the ones that are already, let's say, relatively mature ones. So we're just applying them. But in the future, we need to find the ones that could really fit, let's say, suitable to solve our own problems. Because we're still also learning what are the specific mathematical problems that we are facing. So far, the ones I think we are applying right now are relatively easy ones to me that we could find the appropriate tool.
Okay, great. Yeah.
So it should be a combination of both geochemists and mathematicians. It will be joint work. But I think at this point, I don't think that geochemists have already mastered the data science good enough to be able to raise this very specific request for new algorithms that didn't exist in the market.
Yeah, I think I think a lot of work needs to be, I think, done on the research front, because when I was working in geophysics, the poster that I presented at American Geophysical Union conference, it was using machine learning to predict for slow earthquakes, right? And the response that I got from my poster presentation, a lot of people were interested into it, but I think I could not really find any research papers around this particular topic, using machine learning to actually predict for, I was trying to predict some material properties that help in the deformation of the crust, right, to predict the earthquake. So I think definitely, I think more ground needs to be covered before there is a request and there are advancements. No other question, I think, from my side. I'm open to take any questions.
Okay, so do you have any questions from the audience? So sending type of question. So could you read for I could read it for him and then you can
Sure.
answer. So Sunny is a Sunny is a junior year undergrad student in geophysics at San University in China. So his question is, what learning path do you recommend to be a qualified, let me see, qualified constant, to a qualified geophysics, let's see, geophysicist, sorry,
Understood.
let me
Yeah,
put the
I
chat.
I
Do you
understood.
see it?
Yeah. So the question is, what learning path do you recommend to be a qualified data scientist? If I'm an
Mm.
undergraduate majoring in geophysics now, is it
Yeah, yeah, yeah.
statistics, math, or CS in masters? So I think for data science, right now the field is evolving, and if if you are already in computer science, then it makes sense to go into computer science masters. But if you are in, say, a scientific field such as geophysics, I think first thing is to brush up on the statistics. So have a very good statistical understanding, have a good statistical background by taking courses, maybe minor or elective courses in during your course, undergraduate course. But also on the side, do projects, maybe on Kaggle or any pet projects you can find, to get hands-on the tools. So I've seen a lot of data scientists who know, what the problem is, what algorithms need to be used, but very fine points like the ones I talked today, those are missed out on. So in addition to that, you also need to be very hands-on. You need to have very strong coding experience. So I think that's where I feel you don't really require a master in computer science, right? You can go for a master's in data science, or you can go for a master's in statistics, right? So I think Cornell University offers a master's in statistics with data science. And several other universities have also started up opening up data science masters. I think that's a perfect fit, because the tools that you will learn a little bit of computer science, a little bit of statistics. Machine learning will be in depth. Um, how to communicate the results. So you'll also get a business perspective. So I think for a data scientist, there are different kinds of roles, and doing a data science masters will open up most of those roles. If you want to be a deep learning researcher, right? If you want to work in computer vision at Facebook, or if you want to, work in a very core computer science area, I think that will require a PhD or a master's in computer science, because that field is heavily like filled with computer scientists. But for a data science, I mean, if you want to work on recommendation engines, or you want to work in a lot of different problems, I think data science, doing a master's in data science is the best choice. I hope I answered the question. Okay.
Okay, I have a rather question. So what's the requirement for you for your for the Nissan Digital Center here to hire new employees?
So at Nissan, we look for people who can, who have all the prerequisites. So statistics, coding, having gotten their hands dirty with data. All of those are mainly important. And we mainly look for a strong knowledge of the fundamental concepts of machine learning. So those are the main requirements. As of now, actually, we are not hiring because of the COVID situation. So the team is very conservative. I mean, it's the same team, but in the future, when the situation gets better, I think we will start opening up again. So I mean, we are definitely looking out to increase the team, and we'll be actively hiring when when the situation gets better. So I mean, that is there, but let's hope for the best.
Okay, I think this we're already taken 2 hours from you. Thank you very much, Anant, for your sharing, for the insights. And so Arka, do you have a question?
Yeah. Actually, I had a question.
Yeah,
So
please
I'm
go ahead.
Orko Shahu. I'm a postgraduate student of Jadavpur University, India. So most of my answer you answered while you were answering Sani's question, but one thing I want to focus on is that I want to learn the applications of machine learning and data science, but I want to apply it into geochemistry or like into geoscience. So I really don't want to get into a master's degree in data science or something in computer science. So what to do suggest for me? So because a lot of the self-learning platforms, they mostly focus on sales data, or while they're showing the practical applications, they on sales data or some business models. So it's
Right.
there's a lack of scientific modeling in YouTube or anything, any Udemy or wherever I go. So what would you suggest for me?
So I think the best, since you are like a postgraduate researcher, I mean, you will be strong in research. So I think if you start reading certain papers on how machine learning is being used for the sciences, right? How they are formulating the problem, what all features and how they are extracting it, I think that will be very helpful for you. So the general platforms can be good for learning the tool, maybe learning Python or learning the techniques, but for being able to formulate the problem, right, and being able to understand and like say that this is the feature that I need to create for for this geoscience problem, you should, I think, look at certain papers that I've already done. I remember during my time at University of Minnesota, um, Dr. Vipin Kumar was a professor in computer science, so you can look him up on University of Minnesota. He uses machine learning for the geosciences. I mean, he's into computer science, so the approach is very I mean, it's not from a domain expert, right? So but still I think the research papers might prove useful, because there you can see how the features are created and then what models and what evaluation methods are used. So when you're trying to apply it to geoscience, I think that's a very scientific field, right? Lot of domain knowledge and expertise you would be able to then mold into what you want and what you need from the solution. So I think reading is the best way to go about it, and keeping the learning platforms as just references.
Thank you for your suggestion.
Sure.
Okay, and with that, let's wrap it up. Thank you very much, Anant, and thanks everybody for participating. And have a good night.